Okay, let's discuss ions and ionic compounds. Cations are positive ions, and remember, because the number of protons in the nucleus always stays the same. Indeed, in any chemical reaction, the nucleus is unfazed. Chemistry is really about the electrons. The way ions get formed is by gaining or losing electrons. For a positive ion to be formed, the substance has to lose one or more electrons. Take, for example, sodium. Sodium is a very reactive element, and often it reacts by losing an electron to form the sodium cation. Notice that sodium with 11 protons and 11 electrons is electrically neutral, whereas the cation only has 10 electrons to balance the 11 protons, so it has an overall +1 charge. It's also significantly smaller than the sodium atom from which it came, and we give it the symbol Na+. A group elements in the periodic table only form one kind of cation. The A group elements, which are pictured here, are important because the number next to the A indicates for these elements the number of valence electrons. Those are the electrons that actually do the chemistry, the outer or valence electrons. So every element in group 1A, the alkali metals, all have one valence electron. All the alkaline earths have two, and so forth. And so it might not come as a surprise that all the alkali metals form +1 cations exclusively. Lithium is always either the neutral element or the +1 cation. Likewise for sodium and the rest. All the group 2A elements, all the alkaline earths, all form +2 cations. You may recognize magnesium and calcium as hard water ions. And aluminum always forms +3. Others in the group also can form +3, but aluminum is consistent at +3. So when we name the A group cations, we just give them the name of the element from which they came, the metal from which they came. B group, on the other hand, are a little trickier because many elements in the B group can take on different charges depending on the situation. And so in that case, we have to be explicit about what the name of the element is. So in this case, we have to be explicit not only about the name of the element, but what its charge is. So this is chromium, and in parentheses, I use the Roman numeral 3 to indicate that this is chromium 3. Chromium is a transition metal, and it can take on at least two different charges depending on the situation. This is iron, and its charge is 2. So in parentheses, I write the Roman numeral 2. And finally, we have silver, and this is going to be silver 1. Now, silver only forms the +1. And in fact, other transition metals only form one kind of ion. But for the sake of simplicity, our rule in this course is that if you're naming a compound with a transition metal ion in it, you need to indicate the charge on the ion. So even though zinc only forms +2, you still need to call it zinc 2. Likewise, if you're naming an A group metal cation, you do not indicate the Roman numeral because those names are unambiguous. All alkali metals are +1, all alkaline earth metals are +2, and so forth. So that's the rule. If there are transition metals, you need to indicate the charge. If we give you a transition metal compound, one way or another, we will have to indicate the charge. Okay, in the case of anions, these tend to be the elements in the upper right corner of the periodic table, the so-called nonmetals. In the case of anions, they gain a negative charge by gaining one electron. And the result, as you can see here, is typically a species which is much larger than the atom from which it came. So chlorine has 17 electrons and 17 protons, but by gaining an additional electron, chlorine now becomes the chloride ion, IDE, we'll talk about that in a second, and it increases in size substantially. So, for the A group elements, again, we only have one kind of monatomic ion that can form. Again, monatomic single atom ion. and that's going to be consistent with the position in the periodic table. All monatomic anions end in IDE. That's important. They end in IDE. So if you look at the upper right corner of the periodic table, where the nonmetals are, you see a whole series of monatomic anions. Notice all the halogens form -1, all the 6A group form -2, and 5A forms -3. As I said, this number is in fact the number of valence electrons. And the elements under 8A are the noble gases, which have in common the fact that they have 8 valence electrons, which is a particularly stable situation because, as you can see, the stable anions that form from the halogens all take on 1 electron so that they have the 8 that their nearest noble gas neighbor also has. The 6A take on 2 for the same reason, and the 5A take on 3. So their charges are unambiguous. Anything in column 6A will form a -2 anion. Anything in 7A forms -1, and we call it IDE. So this is hydride. These are nitride, oxide, and fluoride. These are sulfide and chloride. Selenide and bromide. And finally telluride and iodide. All IDEs. And the charges, again, are unambiguous based on their position in the periodic table. All right, anions can also be polyatomic, however. Remember, covalent bonds involve shared electrons, and they're typically very strong. And so you have 2 or more of these atoms bound together such that the total number of electrons is not equal to the total number of protons. In the case of anion, of course, there are more electrons than protons. And those create the polyatomics. There are some polyatomics which have common names which end in IDE, and 2 of them that we may run across this semester are CN, which is cyanide, and OH, which is hydroxide. Again, they end in IDE even though they're not monatomic. The exception proves the rule. The polyatomics, on the other hand, are typically oxyanions. And by that we mean that it's an element, typically a nonmetal, but it doesn't have to be, surrounded by 1 or more oxygen atoms. They're polyatomic ions, again, because they consist of a number of atoms covalently bound together with a charge of typically -1 or more. Their names end in ITE or ATE, as opposed to the monatomics, which end in IDE. And that's an important distinction. So, let's take a couple of examples. CO32- is known as carbonate. NO3- is nitrate. Both end in ATE. Now, as I said, you can also have an ending ITE. And what ITE indicates is that there are 1 fewer oxygen atoms than there are in the polyatomic with ATE at the end of its name. NO2- then is nitrite. So once you know the formula for the ATE version of that particular polyatomic, you know the formula for ITE. Notice, by the way, that the charges are both -1. And that's true consistently among a group. Another example of this is phosphate. PO4 3-, that's phosphate. ATE, and PO3 3- is phosphite. ITE, ATE. Now sometimes a situation arises where you have more than two possible polyatomics in a given family. That situation arises actually for all the halogens. So if we take ClO4-, it turns out in addition to ClO4-, there's also ClO3-, ClO2-, and ClO-. So there are 4 oxyanions in the chlorine family, and the same is true for iodine and bromine. So we need more than just a suffix to name these. Again, the one with most oxygen should end in ATE, but in order to distinguish it from all the others, the one with the most oxygen also has a prefix PER. So this is perchlorate, ClO4-. Down from perchlorate is chlorate. We drop the prefix. Below that is chlorite. There's the ATE, ITE thing again. And the polyatomic with the lowest oxygen count is hypochlorite. So when you have oxyions containing a halogen, because there are 4 possibilities, you need a prefix as well as a suffix so you can distinguish all 4. Common polyatomic ions are given in Table 2.5 of your textbook, Silberberg. And again, the ones in bold are ones you should pay particular attention to. Notice also, by the way, that as I just illustrated, if you know one, you know the one right next to it. If you know nitrate, you know nitrite. If you know sulfate, you know sulfite. But the ones in bold are the ones you should focus on most because it's the ones we'll use the most. Acetate, by the way, is an interesting case. We'll tend to refer to it in this form just because it's more informative in terms of what the substance is really like. It's actually the anion form of acetic acid or